of science. The first is taking something that we think is impossible, as the previous speaker showed in his work with respect to the diffraction barrier. Coming as an engineer who was trained in IIT Madras, I want to show that we can do something with a naturally occurring material that has previously been thought to be impossible. So I'll start with that. The theme of that first part of my presentation is to show how in the last 10 years, very different disciplines have come together in ways in which we could not have imagined even 10 years ago. And what does it mean? What does it mean for the future, especially for the younger students who are here, or younger faculty members who are here? In the course of your lifetime, some of the possibilities that you have are quite significant. The second part of my talk, because the theme of this Indian Science Congress is also rural development, and we are here in an agriculture university, I want to talk about technology in the era of the fourth industrial revolution, and what are the positives and what are the potential negatives, especially for a large and populous country such as India, and what are the implications of science on society. So those are the two aspects of my presentation in the next few minutes. So the title of this is Science Across Disciplines and Consequences for Industry 4.0. Next slide, please. So the first part, as I mentioned, I'm going to talk about unprecedented convergence of different scientific disciplines. So what is so special at this point in time compared to, say, 10 or 20 years ago? Here are some examples of this. We can fabricate nanostructures. Because of nanotechnology, we can fabricate nanostructures to a precision of 1,000th to even much, much smaller than the thickness of the human hair. We can manipulate it, and as the previous speaker showed, we can also image it. So that gives us unprecedented power to look at materials, to look at nature, and to look at the world compared to 10 years ago. So things that we thought were impossible could be possible, because at very small scales, at the nanoscale, nature behaves very differently than at much larger scale. So that's the first point. We can manipulate them, we can characterize them. In addition to that, because of power of computing, in the last 20 years or so, our mobile phone has much more computing power than the Apollo program computer that went into space. So that gives us an ability to calculate things that we cannot experimentally do, that will guide our experiments for the future. When we combine experiments and computations, it's even more powerful. So that gives us even more opportunities. Now add to that, just in the last few years, the emergence of artificial intelligence and machine learning, deep learning from massive amounts of data and data analytics, and that's going to impact every field of science in the next 10 years. It's already starting to do that. So what does it mean for physics? What does it mean for material science? What does it mean for chemistry? So I'm going to show you some examples. What does it mean for energy research, optoelectronics, and so forth? So I want to show you some examples. So most of what I'm going to talk about is work done in the last 2 years, published in the last 2 years, very recent work in these areas that I just highlighted. So the implication of all of this is we can design new materials that we thought were impossible, and I'll give you some demonstration of that. Devices, properties of materials, and we can do performance of existing materials because of the combination of these 4 factors that were previously not possible. And this is for structural applications, major material systems that we use to build buildings, transport systems, etc., bridges, etc. Or it could be functional materials that go in small devices like computer chips or energy systems. Or it could be in biological materials. I want to show examples in engineering systems and biological systems. So that's the first part of my presentation. Next slide, please. The second part of my presentation, I would like to focus on what we call the fourth industrial revolution, or Industry 4.0, which is now impacting global society unlike any other previous industrial revolution. So what is Industry 4.0? The Industry 4.0 is the convergence of the physical world, the digital world, and the biological world all in one. So what do I mean by this? So let me give you an example. Suppose you need a new hip implant. You can take an MRI image, you can take an X-ray image. From the X-ray image, you can measure the dimensions of your body. You can look at the density of your bones, and you can make a computer model out of this. You can digitally 3D print, either with a metal, like a stainless steel or a titanium, or with a ceramic, such as hydroxyapatite, or with a plastic or polymer, such as ultra-high molecular weight polyethylene. You can print the implant to your own biological body shape and size. On top of it, you can embed a computer chip into the implanted device, connect it to your mobile phone. Every time you walk, the G-force in your phone that measures your step can measure your gait. So after the surgery, if the implant doesn't work, if the phone can pick it up, alert you and your doctor. So that's a convergence of the physical, the digital, and the biological worlds. That's one example. There are many, many other examples of this. You can also do your personalized genome sequencing, look at the consequences of this. So there are positive to this, there are negative to this. So that's the fourth industrial revolution. It's already beginning to impact the world. So what are the consequences? And what drives the fourth industrial revolution are science and technology involving robotics, artificial intelligence, machine learning, data analytics, Internet of Things, personalized medicine, precision medicine, autonomous systems, mobility, autonomous mobility. All of this is related to science and technology, but it also involves policy, economics, ethics, and so forth. So, especially in the context of rural development and technology, science has a major role to play, but science alone will not be enough. So that's my point of the second part of my talk. The first part of the talk is all about basic science. The second part of the talk is the fact that science alone is not enough. Science applied badly can be bad for society if you're not careful. That's the message of the second part. But science has a lot of wonderful things to contribute. So let's look at technology, the unprecedented pace of change. So I want to give you some examples. When the telephone was introduced, it took 75 years to reach the first 50 million customers for the telephone. 75 years. When the car was introduced, the automobile, it took 64 years before 50 million people bought a car. When electricity was introduced, it took 46 years. Still, many parts of the world don't have electricity. Credit card, it took 28 years to reach the first 50 million customers. Television, 22 years. ATM machines, bank machines, it took 18 years. Computer took 14 years to reach the first 50 million customers. Mobile phone, 12 years. Okay. Internet, 7 years. Just 20 years ago, it took 7 years to reach the first 50 million customers. Facebook took 4 years. WeChat in China took 1 year to reach the first 50 million. And just a few years ago, Pokemon Go reached 50 million customers in 19 days. So that's the pace of change of technology. And that's why the fourth industrial revolution is very different from any previous industrial revolution. So now let's look at the first part. I mentioned about convergence of different fields of technology and what are the implications and why some unexpected things can happen at very small nanoscale that you don't expect at bigger dimensions, macro or micro scale. So I'm going to use one particular example. Take the hardest material in nature, one of the most expensive materials, the most difficult material to extract and process because it's so hard, that's diamond. So diamond is the hardest material. Diamond is also commonly known to be brittle. So what does it mean? If you try to break diamond, of course it's very difficult to break diamond because it's so hard. It's the hardest material found in nature. It's very difficult to break it. But if you do succeed breaking diamond, it's highly brittle. Nothing will happen. It won't even deform. And then all of a sudden it'll fracture. So the question is, the historical question is, if diamond is so brittle and the hardest material, can you bend diamond? So what I would like to show is you can indeed bend diamond. This is what we found last year. So I'm going to show you videos of how to bend diamond and why we bend diamond. And then ask the question, so what? Okay, you can bend diamond, so what do you do with it? What are the implications of this? So bending diamond and implications for devices is the first part of what I would like to demonstrate. As a consequence of this, nanoscience can inspire the design of engineering of materials, new materials, with properties that we think are not possible today. And I'll give some demonstrations of this, and discovery of new material properties and performance. So here is the experiment that I want to describe. But before I describe it, it's truly an international team that worked on this for 3 years. So I want to see, let me see if this works. At the bottom, in the bottom row, you see this was a paper that was published in Science last year. Wai Lu is a young professor who was my former postdoctoral fellow, who's in Hong Kong. So he and his group made diamond synthetically, chemically. So you take a piece of silicon and you use chemical vapor deposition on top of it to form a very thin layer of diamond. And then you use a technique called pulsed electrodeposition to create nano needles of diamond. So these are needles that are sticking out of the surface of a piece of silicon, a plane of silicon. And the length of the needle, so the diameter of the human hair is 80 micrometers. The diameter of these needles is about 80 nanometers. So it's 1,000th of the thickness of the human hair. And the length is about 200, 300 nanometers. So that's the dimension of the diamond needle. So we made these needles. So okay, you have these needles. How do you demonstrate that you can bend diamond? How do you bend it? So we took it to a microscope. So you can take it to an atomic force microscope. And most universities in the world have them. So you take the silicon with a diamond needle sticking out of them. You put it in the microscope. And then you have a diamond tip that comes. So the needle is here. The tip is coming here. You bend the needle like this. And what we would expect, if you had a long piece of diamond, which you can see with the naked eye, if you try to bend diamond, nothing will happen. It won't even bend, when all of a sudden it'll break. So what I would like to show you is at the nanoscale, nature behaves very differently than at the macro scale or even the micro scale. So why does it do this? At the nanoscale, the surface area to volume is very high. At the macro scale, you have very large volume relatively small surface area. At the nanoscale, you have large surface area and small volume. So when you have a large surface and a smaller volume, you have less defects in the system because the defects can come to the surface and leave. Secondly, when you have a nanoscale material, you can create atomically smooth surfaces. So because of that, you have very little defects. When you don't have any defects, things behave very differently than in the macro scale. So diamond at the large scale breaks because when you make diamond, you have defects. Even natural diamond has defects in it. That's why the price of diamond depends, and the color of diamond depends on what defect content there is. So by going to the nanoscale, you can eliminate the defects. You can create smoother surfaces. Therefore, it can behave very differently like a metal. So let's see if it works. So what you see here are images taken in the microscope. So your top left, you have a diamond indenter inside the microscope, and you have needles sticking up on a surface, and you can see the scale is 5 micrometers. So 5 micrometers is like 1/20th of the thickness of the human hair. If you go to atomic resolution, so you can actually see at the top right, 0.2 nanometers. So you can see individual atoms of carbon. Diamond is made of carbon. So you can see atoms of carbon. It's a very smooth surface. And this synthetic diamond is very much like natural diamond. So in the figure C in the middle, you have the diamond needle sticking up. You come from the top surface. You bend it with a diamond tip. And then it'll fracture eventually. So let's see how it works. So here is left is a movie, right is a computer simulation of the same experiment. So the tip comes in. You can see how much the diamond needle bends. It bends almost like aluminum. Okay? And then if you retract it, it'll go back to its original shape. So this is what you call reversible large elastic deformation. And on the right, because diamond is elastic, but it's large deformation elastic, so you can use nonlinear elasticity theory to do a simulation very accurately, allowing for the anisotropy of diamond and large deformation of diamond. And what you find is something very remarkable. You see the strain, the maximum strain in the red color on the right is 0.09. That means it's 9% strain. So diamond is supposed to break at 0.1% strain, bulk diamond. But if you go to nano diamond, you can actually get 9% strain in diamond, which is quite remarkable. So when we first found this, we didn't believe this. So we went back and said, redid the experiment many, many times. When we sent it to Science, the reviewers wanted to know, is it really true? So can you show in the electron microscope that the atoms are exactly the same as in the natural diamond, which we did. Then they wanted to show the surface. There is no amorphous layer on the surface. Then they asked all kinds of questions. Can you do the defect calculation? So after all of this, this is what we found repeatedly. Now, if you go beyond 9%, let's see what happens. So if you go beyond 9%, it breaks as it's expected to break. And you see the angle of the surface, that's exactly a particular plane of diamond called the cleavage plane of diamond, which we know exactly. So you can get a lot more information out of this. So what we found was that something really unexpected. You can actually bend diamond just like a piece of metal, but only at the nanoscale. And if you can do this, there are a lot of possibilities. Then there is a question. Okay, you're doing the experiment inside a microscope. You have diamond on diamond in vacuum, almost in vacuum. Is there friction? What is the effect of friction? Okay, we try to address that. So we did a friction calculation. Friction coefficient of 0.1 or friction coefficient of 1. And what you find is that depending on the size of the needle, you can get up to 9% strain, and the friction has absolutely no bearing on whether it bends or not. So we convinced ourselves of this. And these were single crystals of diamond, just one grain. You can also do polycrystals, many grains attached together. So when you do the experiment in polycrystal, as shown in the blue data points, you still get a very large amount of strain, 4%, which is quite remarkable. So when we did this, we found that at the time of publication of this work in April of 2018, this was the highest strength ever demonstrated in any material in 3D. People have demonstrated a higher strength in 1D, which is carbon nanotube, or 2D, which is a graphene layer, but not in 3D. So we did this experiment. So after we published this, so Banerjee was a student, an Indian origin student in Hong Kong, who did the experiments on this. So after we published this, there was a group in China, in Hangzhou. They got excited by this result, so they decided whether they could duplicate this experiment. So of course, science works when somebody else can reproduce your results independently using a different technique. So we did synthetic diamond. They have more money than we do, so they decided to go buy natural diamond. So they bought a piece of natural diamond, they cut it into nano pillars, and then they did an experiment, try to bend it. So you can see in the bottom right, that's a piece of natural diamond of a particular crystallographic orientation where they could actually bend it like this. And we found a strain of 9%, maximum strain. They found a strain of 9.3% before it broke. So this gave us more confidence. So we are now working with them on how to combine our two techniques so that we can expand on this further. They also did other experiments. They indented diamond with diamond and showed that it can actually be indented in the nanoscale. So there are a lot of rich data that came out of their experiments as well. And their paper is about to be published in Nature very soon. So with all of this, the question is, so what? You can bend diamond. What do you do with it? Okay. It turns out that diamond is not only the hardest material that nature produces, diamond is also the best semiconductor material you can possibly find for all kinds of electronic applications and energy applications. It's also a biocompatible material. It's made of carbon, except that it's commercially useless right now. It's so difficult to do anything with diamond, you can't do anything with it. So if you can manipulate diamond, what are potentially some of the benefits you can get out of diamond? So around the time we did this work, two of my former students did another experiment which was quite interesting. They took the commercially most viable semiconductor material, which is silicon. So we all use silicon in all our computer devices. They took a piece of nanosilicon and they found they can actually pull nanosilicon to a strain of 16%. So if you can pull silicon to 16%, you can bend diamond to 9%. What are the implications for the future of microelectronics, optoelectronics, solar cell devices, and many other applications? So here is a figure that shows how electronic materials work. So if you look at this figure, you have silicon somewhere here. Since this doesn't work, I'll point here. Silicon is here. Diamond is over here. Silicon has something called a band gap of 1.2. It's the most commercially friendly material. Diamond has a band gap of 5.6 electron volts. Okay? It's called ultra-wide band gap. All the other materials are in between. These semiconductor materials also emit light. So you can see the colors in a rainbow. By changing the band gap, by changing the bond energy, you can change the color. That's how lasers work, color of lasers work. So if you can modulate the band gap of a material, you can also modulate its optical properties. You can modulate its color. You can also control whether it's direct or indirect band gap, and you can control your semiconductor applications. So this is the practical use of it. In 1988, IBM and Intel commercialized something called strain silicon. They put 1% strain in silicon. Now that's now a $350 billion industry. So if you can modulate a microelectronic component with 1% strain, what can you do with 9% strain or 10% strain? How much improvement can we get? So potentially the applications are quite significant. And silicon is not only the most widely used electronic material, it's also the most widely used solar cell material for alternative sources of energy. So then there is something called figures of merit in the microelectronics industry. So if you compare silicon, which is the most manufacturing friendly material today, to silicon carbide, which is used in some applications, to the most unfriendly material, that's diamond. And if you look at the different metrics that the microelectronics industry looks at, here are the relative merits of it. If you look at high frequency capability, it's called Johnson's figure of merit. If silicon is 1, silicon carbide is 215 times better than silicon, and diamond is 81,000 times better than silicon. If you look at the third one, FET switching speed, switching of electronic systems, if silicon is 1, diamond is 3,595 times better than silicon, but unfortunately it cannot be manufactured. So going back to the previous figure, if you want to change the band gap, if you want to change the optical properties and color, and if you want to change other applications, currently what do? You change the chemistry. But can you change all of this without changing the chemistry? How would you do it? That's where our work comes in. You don't have to change the chemistry. You put a strain, a mechanical strain, and in a thin layer, if you put a strain of 5% or 8%, you can change the band gap. At least that's theoretically, that's what we would expect. Can you do it? So, and how do you do it? And how do you prove you can do it? So last year, when this paper came out in Science, several TV outlets interviewed us. So they asked, how are you going to prove it? So that got us working. So we decided we're going to do a calculation to show that it can be done. Then we quickly realized that's not workable, because to do that calculation, the fastest supercomputer in the world will not be enough. Because if you take all the atoms, and strain is 6 dimensions, you take 6-dimensional strain space, and you calculate all the strain energy that's stored, and you minimize the energy, what is the best way to strain diamond or silicon? It's impossible to do. It'll take months and months in a supercomputer. It's not possible. So how do you do it? So we decide, but it has to be based on physics. It cannot be based on just computing. So we decided we'll take an existing technique called DFT, density function theory, that's very well known in physics, using quantum mechanical calculations. Take 1,000 calculations. So if you do in a brute force way in a supercomputer, you will need more than 1 million calculations, and it's not possible. Realistically, it's not possible. So we decided we'll take DFT and make 1,000 calculations and take artificial intelligence and deep learning and train the neural network. And once you train it with 1,000 data points, you ask the neural network to tell you how quickly you can go from one band gap to another and what kind of strain you need in 6-dimensional strain space. That's very doable. You can do it with a few laptop computers combined together. So that's possible. You can even use mobile phones combined together to do that. So we did that last year. So I want to show you what that means. So this is the work. This is also a very international team. So the last author, Ju Lee, And the first author and the middle author, Ming Dao, they are all my former students and postdocs and collaborators. They are all at MIT in Boston. The two other authors are Russian authors in Moscow. They are mathematicians who do neural networks. So this group, within 3 months, figured out how to do this. So this was published early last year in the Proceedings of the US National Academy of Sciences to show that you can actually take silicon, which has a band gap of 1.2 electron volts, and you can turn silicon into a metal in the fastest way. And in 6-dimensional strain space, how do you figure out which strain to put? So that's the outcome of it. We've also taken diamond and showed that diamond can be made to behave like a commercially used compound semiconductor, where it can go from a band gap of 5.2 electron volts to something close to 2.5 electron volts. So that's very much possible. So here is the example for silicon. So you can take a band gap, and you can see the red dots that's going down on your left. You can go from a band gap of 1.2 electron volt to 0. In other words, you can make silicon behave like a metal in the shortest possible way with the least amount of strain, and we know exactly what strain to put in. And the error involved compared to calibrated experiments is 3% using neural networks and machine learning and DFT calculations. For diamond, it's 3.2%. So for a 1.2 electron volt band gap, the error is 8 milli electron volt. So it's highly, highly accurate experiment. This is for diamond, the fastest way to reach diamond band gap of something like 1.5 or so. So this is what we do with bending diamond. So potential applications. So this is what we call elastic strain engineering. We can bend diamond, and we can use that for a variety of applications in electronics, microelectronics, energy systems, etc. Bioimaging, biosensing, drug delivery, data storage, nanomechanical resonators, microelectronics, etc. These are potential applications of this technique. So subsequent to this work, I mentioned the group in China. There are several other groups that have taken up this work, and they are looking at the implications of this. So I want to give you one more example before I go to the second topic. In biology, in cell biology and human diseases, how can we bring biology and medicine in contact with engineering and physics so that we can take diseases? So I want to pick a disease that affects parts of South India, especially parts of Tamil Nadu, where there is a disease called sickle cell disease. It's genetically the most precise disease. Sickle cell disease occurs because of one genetic defect. It depends on whether you inherit from one parent or both parents. In the 6th position of the amino acid, when valine substitutes for glutamic acid, you have the sickle cell disease. It's precise, genetically the most precise disease. You can test it. If you have the sickle cell disease, there are consequences of the disease. So the next slide shows that. But before I go to this, let me go back to this figure. This is a picture drawn by, it's a paper we published in 2010. One of my former students at MIT, Young-Kyun Park, who's now a professor in South Korea. It was his work, and as shown in the cover of this journal, this is a live human red blood cell, the red disc that you see. The diameter of the red cell in our body is about 1/10 of the thickness of our hair. In our body, 42% of the volume of blood is red blood cells. That's why the color of blood is red. Every second, our bone marrow produces hundreds of thousands of red blood cells. They circulate through the body. They deliver oxygen to different parts of the body. They take carbon dioxide back to the lungs. That's their only role. Why does shape and mechanics matter? The diameter of the red blood cell in our body is 8 micrometers. The smallest blood vessel in our brain is 3 micrometers. So an 8 micrometer disc has to squeeze through a 3 micrometer tube in the brain to deliver oxygen and to take carbon dioxide back. That means it has to stretch. A red blood cell lives in our body for 120 days. During the course of the 120 days, it circulates millions of times, just delivering oxygen, taking carbon dioxide back. If it loses its ability to stretch, we get a disease. So malaria is another disease that affects India quite a bit. In severe forms of malaria, one of the fatal forms of malaria is cerebral malaria. Brain doesn't get oxygen. That's why people die from malaria. And one of the consequences of that is the red blood cell is not able to stretch in severe form of malaria in the human body. So this is the consequence of shape and deformability. Let's go back to sickle cell disease. So people who are born with the sickle cell trait, when they inherit from their parents, usually it affects people of African origin and people of Asian origin. Parts of India, Bangladesh, Sri Lanka are affected by this. So in a normal blood, as shown in your left, when blood is in the deoxygenated state with low oxygen, when it goes back to the heart and the lungs, it's a disc shape. But if you have a sickle cell disease, when the oxygen pressure is very low, the cell is no longer disc shape, it becomes more fiber shape, like a sickle shape, and hence the name sickle cell disease. So, and that's because of a genetic disease defect, because of one defect in chemistry due to birth. So as a result of this, these fiber-shaped blood cells get stuck in the blood vessels. They are not able to move. As a result of this, there is a crisis called vaso-occlusive crisis. It causes very severe pain. So the lifespan of people with sickle cell disease is much lower than the lifespan of people without the sickle cell disease. So as a result of this, in severe form, when the people have the sickle cell pain crisis, you have recurrent pain episodes. In severe forms, you get stroke, organ damage, different organs in the body fail, swelling of hands and feet, and the picture that you see is of a young child who has a sickle cell disease and a pain crisis, and you can see the swelling of the hand due to the pain crisis. So I want to demonstrate how engineering and physics can help in this area. There is only one FDA-approved drug for this. It's called hydroxyurea, and it's not that particularly effective for all the patients. So what we did with a group of medical doctors a few years ago was to create a microfluidic device in the lab. So you see the circles here. These are the red blood cells from a sickle cell patient. So we get blood from a patient who has a sickle cell disease. We put it outside the body in a little device about the size of a thumbnail. It's a tiny device. You put the red blood cells in there, and then you control the oxygen pressure in the device. So you start with what is called normoxia, normal oxygen pressure in the body. So what I'm going to show you a video clip here, and what you see here is that under normal oxygen pressure, the cells are circular or disc-shaped. As you slowly start to reduce the oxygen partial pressure, you can actually make the blood sickle in the device outside the body. You can calculate the time for sickling. You can calculate the time for unsickling. You can connect the kinetics of the sickling with the pain crisis. Then if you want to give a drug to the patient, you don't give the drug directly to the patient. You give the drug to the patient's blood in the device first to see how it works before you administer the drug to the patient. And you can do that for other diseases as well. So that's the goal of this. Can you click on the video, please, in the middle? Please play the video. Hello? Here you go. So you can see that when you reduce the oxygen partial pressure, you can see the sickling in, and you can see the shape. And you'll see very soon, when we reintroduce the oxygen, it will very quickly go back to its original shape. So what does it mean? So I'm going to demonstrate in this particular video what it means for the human body. Of course, we can't do the experiment in the human body, so we get blood from the sickle cell patients. We put that into a microfluidic device. So what you're going to see in this video is from your right to your left, we're going to send blood cells, red blood cells, of the sickle cell patient. We're controlling the oxygen partial pressure. Now we're going to slowly reduce the oxygen concentration, and then you'll see the blood cells that are going through will begin to get stuck. So please play the video. So this is under normal pressure, normal oxygen pressure. We reduce the oxygen pressure. Now you'll see the blood cells starting to get stuck, and very soon you'll see on the right-hand side more and more getting stuck. This is the origin of, there is no chemistry here. This is just a demonstration in the lab, in a little device. This is what causes vaso-occlusive pain crisis. And then you reintroduce oxygen, you'll see what happens very quickly. The time for unsickling is 1/10 of the time for sickling. That is directly connected to the pain. So we can quantify all of this using engineering. So what I've shown you in the diamond example on this is we can get some unexpected things by bringing very different fields together, and we can combine different developments in different fields that cross across many disciplines. So let me just finish then with, in the next few minutes, with the last part. What does science mean for the fourth industrial revolution? What are the positives and what are the negatives? According to McKinsey, the 12 disruptive technologies that will impact the next 5 to 10 years, where for trillions of dollars, will be these 12 technologies. The most significant is mobile internet, especially with the soon-to-be introduced 5G technologies, cloud technologies, next-generation genomics, advanced materials, etc., Internet of Things, renewable energies, and so forth. What is unique about the fourth industrial revolution? 3 things. First, unusual pace of development. I showed you earlier it took 75 years for the telephone to be adopted by first 50 million people. Facebook took 4 years. So the pace of development and adoption on a global scale is much faster now than ever before. Second, the individual citizen of the world, you and me, doesn't matter whether you come from a rich country or a poor country, it doesn't matter. We have an opportunity for the first time in history to connect, engage in a two-way communication from mobile technology to the cutting edge of revolution. You can receive information online if you have access to the internet. You can also provide data from your mobile device, from your implanted device, from your heart valve, from your car, from your mobile phone, to the cutting edge of the industrial revolution. That has been unprecedented. The third, for the first time in human history, there is a question about whether humanity will change because of technology. That has never happened before in the most fundamental way. This is the most important part to me of the fourth industrial revolution compared to the 3 previous industrial revolutions. Do we run the potential to lose some basic characteristics of humanity, issues of inequality, especially if technology doesn't benefit hundreds of millions of people, it benefits only a few, it is not going to be successful in the long run. Especially for a country like India, it's going to be very, very critical. Whether technology benefits the large fraction of the population or not is going to be extremely critical. Countries like India, China, and Africa, 3 examples where it's going to be a very critical question. Humanity, machines cannot do certain things that we can do today. So the question is, can machines ever do some of the things that we can do today? So I'm going to take one example of, let's take the example of dignity. Dignity, you can take an Indian from India, you can take an Indian from the Middle East, Indian from UK, Indian from the US, anywhere in the world. Everyone has dignity. But individual person's dignity, even in the same family, is going to depend on their individual circumstances, how they grew up, what their family was, what their values were. That's so individualized. But when you take massive amounts of data and aggregate it, and machines make decisions based on this, will they ever understand what dignity means for you, what dignity means for me, which could be very different? We both have dignity. And how do the machines distinguish that when you have millions of data points? And this is a very critical question for the fourth industrial revolution. So I'm going to summarize 6 issues that are going to define where fourth industrial revolution is a success or not. First, job creation versus job destruction. Machines are going to replace jobs. Every previous industrial revolution has done that. Fourth industrial revolution will do it faster and in larger volumes. But every previous industrial revolution also created more jobs than it destroyed. Sometimes it took 50 years, 70 years. With the rapid pace of change, now nobody has the patience to wait 50 years. So it has to happen quickly. So what does society do? What do governments do to make that happen? That's going to be very critical. If there is a large time lag, it's not going to work. So development and inequality in the context of the fourth industrial revolution are going to be critical. Second, what does it mean to be an educated person in the 21st century? If you're 18 years old and graduate from high school, or if you're 22 years old and graduate from university, you acquire a basic knowledge, but you're going to live longer and you're going to change jobs and professions many, many more times. When you have a university degree, does it prepare you to change jobs for the next 50 years, even in different professions? What is the minimum body of knowledge you're supposed to possess? Do universities know what to teach you today so that you're prepared for the next 50 years? I don't think any university has completely figured it out anywhere in the world today. Definition of being human. If machines make more and more decisions, what does it intrinsically mean to be human? And do we know what that is? And this is going to be a greater and greater importance question in the next decade or so. And this is something we all need to be prepared for. So there are people talk about the so-called point of singularity, when machine decisions become almost as good as human decisions. Some people claim it'll come by 2040. Some people claim it'll never come. But let's assume it comes at some point in the future. If it happens, will we reach a point where machines make a decision so quickly based on so much information that we as humans cannot overrule the machine? It's too late to undo what the machines have decided to do already. Will we ever reach a point? If so, what do we do about it? How do we undo it? Humans, we know, have biases. There is discrimination all over the world. Gender bias to every form of bias. Will machines increase the human bias or reduce the human bias? Already there are indications that machines at least have the same level of bias as humans too. Probably if you feed in wrong data, you can increase the bias of the machines. For every intended benefit of technology, there are unintended consequences. So the US National Academy of Engineering last decade, published 20 greatest engineering achievements of the 20th century. Electrification, commercial aviation, nuclear power, creation of the internet, air conditioning, etc., microelectronics. Then 3 years later, they published another list called the 14 grand challenges of the 21st century. Climate change, carbon sequestration, containing nuclear terror, securing cyberspace, etc. So if you put the two lists side by side, all the benefits and wonderful things we did in the 20th century, many of them led to the grand challenges of the 21st century. So if so, what was missing? What was missing was not to look at the human consequences, the human interactions of technology. So how do we do that better this time around so that the achievements of the 21st century don't become the challenges of the 22nd century? The last point is technology is pushing us to be more and more precise and more perfect. So atomic clocks can tell the time precisely to 10 to the minus 10 of a second. GPS can give you a location very, very precisely anywhere in the world, and it's getting better and better. Everything, you can have nanograms, nanotechnology, and so forth. So with increasing precision and increasing perfection, do we lose? Humans are intrinsically imperfect, and we learn from imperfection. And imperfection also leads to creativity. You have to fall down before you learn how to walk or ride a bike. So will technology push us to be less human because it's pushing us to be more and more precise and more perfect? And this is something that we need to think through very carefully. The cost of precision. We know that already. If somebody sends you an email, they expect you to send a response immediately. If you wait one day, they get impatient. So this is the consequence of technology. So I want to finish with 2 slides. At NTU, we created something called the NTU Institute of Science and Technology for Humanity. It has 3 themes: responsible innovation, governance and leadership with ethics in the era of Industry 4.0, and new urban Asia, because Asia is where all the big cities are, the large populations are, and India is a very good example of this. How do we create this technology? We also decided that we're not going to just talk about all of this, we're going to do something about this. So at NTU in Singapore, we have a campus that's 500 acres or 200-hectare campus, beautiful campus. It's considered one of the most beautiful university campuses in the world. So last year, we made an announcement, a public announcement, that we decided that we're going to make 3 commitments. By 2021, we're going to reduce the amount of energy used on campus by 35% compared to what it was in 2011. While we bring new buildings, we're going to reduce the net waste and net water use by 35%. We are on target by next year to reduce all of this by 35%. If we achieve that, which we will, by 2025, we will reduce each one of that by 50% compared to what it was in 2011. So that's our goal. So we can actually do this. So with this, let me thank you. This is our campus. Thank you.
I request Professor Bhairappa and Professor K.N. Thimayya to come on stage, please.
Thank you. Each time, we get something new. Thank you.
Ladies and gentlemen, in the morning, during the inauguration, Professor K.S. Rangappa, the General President, in his welcome address, described Dr. S. Rajendra Prasad, Vice Chancellor of the University of Agricultural Sciences and Chairman Organizing Committee of the 107th Indian Science Congress, as the ideal team leader. I thought that is the most appropriate description of Professor S. Rajendra Prasad. His leadership qualities proved beyond doubt. Now, I request Professor Rajendra Prasad to come on stage and present a memento to Professor Subra Suresh, who has delivered such a scintillating second public lecture this evening. Thank you, Professor Rajendra Prasad. Now I request Professor Gangadhar, past General Secretary, Indian Science Congress Association, and convener, Bangalore chapter, ISCA, and former syndicate member, Bangalore University, to present a memento to Professor K. Bhairappa, who has chaired this session, the second public lecture. I request again Professor Gangadhar to present a memento to Professor K. N. Thimmaiah, the co-chair of this public lecture. I thank the dignitaries on the dais. Thank you, sir.
Now we are going to... Hello. Now there are 3 ISCA, Indian Science Congress Association, endowment lectures or award lectures. So we will start immediately with the 3 endowment lectures. And I request Professor K.S. Rangappa, the General President of Indian Science Congress Association, to kindly come to the dais. I request Professor Ramakrishna, General Secretary, Membership Affairs, and Dr. Anup Jain, General Secretary, Scientific Activities, to also come to the dais. So we have 3 award lectures, ladies and gentlemen, and I do hope you would stay back for these award lectures. These are very short award lectures. 3 renowned scientists would be delivering these lectures. And after that, we will break for tea. So please, I request all of you to stay back for these award lectures. The first award lecture is B.C. Guo Memorial Lecture. The B.C. Guo Memorial Lecture, which was instituted by the Indian Science Congress in 1965 with a donation from his wife, C. Fullerenu Guho. And the topic of lecture is relevant to the science of nutrition. The lecture carries an honorarium and a plaque. And this year, it is a great privilege that this award lecture is given by Dr. Somnath Rai, who is the former professor of Department of Human Physiology with Community Health in the Vidyasagar University, Midnapur. I request Professor K.S. Rangappa to kindly introduce the awardee, and I request the awardee also to please come to the dais.
Well, it's a privilege for me to introduce Somnath Rai. Somnath Rai is a senior professor of physiology in the Department of Human Physiology and Community Health at Vidyasagar University, Paschim Midnapur, West Bengal. He did his MSc in physiology from University of Calcutta in 1977, obtained PhD degree in 1989. On the thesis studies concerning kinesin malaria from University of Calcutta. Alongside teaching, research has been the primary focus of Professor Roy's scientific career at Vidyasagar University. He was mostly interested in working at the interface of chemistry and biology, using nanotechnology as a tool to fight fatal diseases like cancer. He and his co-workers have also worked extensively on malaria. Very recently, Roy have identified a unique novel mutations in PF-CLATCH gene correlating with artemisinin resistance, raising the alarm of the requirement to revise the malaria control program in India. Major scientific contribution of Professor Roy lies in the field of drug-resistant microorganisms like superbugs and Plasmodium Puram malaria. His search index is 20, and he has published 91 papers in international and national 19 peer-reviewed publications. Professor Roy has also authored several book chapters, the most recent one being the textbook Basic Concepts in Immunology. Professor Roy is the editorial member of the journal BLDE, University Journal of Health Science, published by Walter Clover and Blade University. Professor Roy has been elected as the president of the section of medical science of the Indian Science Congress 2016-17. He has been elected as fellow of the West Bengal Academy of Science and Technology in 2013 for his notable contributions in the field of drug development. He has delivered several invited lectures in international conferences like the 4th Biennial Regional Conference of South Asian Association of Physiologists, Dhaka, Bangladesh in 2014, the 13th annual meeting of the Society for Research in Nicotine and Tobacco at Austin, Texas, USA in 2007, and at the VU IMS International Conference at Bangkok, Thailand in 2012, and also acted as a resource person on various orientation and refresher programs of academic staff college. It is over to Rai.
Thank you, sir. Thank you, Indian Science Congress Association, for giving me the opportunity to present some of my work and presentation of the B.C. Guha Memorial Lecture. So the title of my talk is Genetic Polymorphism . Genetic polymorphism of Plasmodium falciparum genes, which associate with drug resistance in eastern India. So polymorphism is commonly found in nature. It is associated with biodiversity, genetic variation, and adaptation. It always functions to retain variety of forms in a population living in a varied conditions. It is heritable and changed by natural selection, the process whereby organisms better adapted to their environment and tend to survive and produce more offspring. So the theory of natural selection was first fully expounded by Charles Darwin, and it is now regarded to be the main process that brings about evolution. So survival of the fittest is a phrase that originated from Darwinian evolution theory as a way of describing the mechanism of natural selection. So these are the state-wise demographic alteration of chloroquine resistance variation in India. Blue color is chloroquine sensitive, and pink color is intermediate chloroquine sensitive area, and red color is highly chloroquine resistance area. So in our study, we are focusing on a comprehensive picture of resistance in Kolkata, Purulia, Bankura, and Medinipur. Those are endemic districts in West Bengal, and we have designed our study before and after the introduction of ACT. The full name is artemisinin combination therapy, which is introduced in the year 2009 by National Vector-Borne Disease Control Program in India. We have studied these 4 districts, endemic district of malaria, and we have studied 5 genes, mainly PFCRT, PFMDR1, PFK13, PFDHFR, and PFDHPS. So these are the important drugs, and polymorphism of these drugs or mutation of these PFCT drugs actually resistant to the quinoline compounds, mutation in the PFDH genes responsible for the resistance of the pyrimethamine drugs, and polymorphism in the PFDHPS gene responsible for the sulfodoxine drug resistance, and mutation in the PFKILS13 gene are responsible for the artemisinin resistance. So we have divided our study in 3 phases. So in the first phases, selective sweep of the molecular markers in chloroquine-resistant Plasmodium falciparum malaria in West Bengal. So this is the PFCRT gene, this is the transporter, PFCRT transporter, and mutation of the 72, 76, and 1246 is responsible for the blocking of these drugs. And distribution of different PFCRT polymorphism and haplotypes in Kolkata and Purulia before and after introductions of the national drug policy. And we have seen that 72S, which is the red color, and 73, B73, which is green color, and 75, which is blue color, and 76, which is pink color, is gradually increased. That means in year-wise distribution of different allele in Kolkata and Purulia, and the mutation is generally enhanced during 2008 to 2013. And not only that, we have also seen the wild type of allele was gradually decreased. Here we have seen that SBMNT allele, that is in the SBMNT, that is in pink color, and CVIET, that is in sky blue color, is gradually, these are very triple mutant and were subsequently increased in this period. Those are very fatal. So this is regarding PFMDR1 transporter, and mutation in the 86Y, 184F, and 1246Y codon are mainly responsible for closing of transporter channel, which ultimately inhibit drug influx. Like PFCRT gene, polymorphism at PFMDR1 86Y, which is a brown color, and 184 codon, that is in green color, were also increased in subsequent years. And we have also find the wild type allele was gradually decreased, and the frequency of most vulnerable double mutant haplotype, that is YFSND, and YFSNY, which is dark green color and blue color, were subsequently increased in this period. So this is the alteration of in vitro IC50 values for chloroquine against different PFCRT and MDR haplotypes in Kolkata and Purulia during 2008 to 2013. And the solid line is hypothetical and shows the level of chloroquine resistance in vitro. K represents Kolkata and P represents Purulia. And we have seen the IC50 value after the drug interactions is gradually and tremendously increased. We have seen in this red color, which is mentioned in the red arrow. So this is the above mentioned panel are the vulnerable haplotypes. These are very vulnerable haplotypes of PFCRT and PFMDR gene, and these are the subsequent DNA sequences, and these are the gene bank accession number and protein ID number. So this is the second phase of our study. Selective sweep of the Plasmodium falciparum antifolate resistant gene in West Bengal changes over time. So sulfodoxine pyrimethamine is the combination, is the most widely used antifolate to treat chloroquine resistant falciparum malaria. Because of their synergistic effect, the combination is more effective than either drug used alone. And here we have seen that sulfodoxine, which inhibits the DHPS gene, and pyrimethamine, which inhibits the DHFR gene. And so parasite cannot utilize the folate for its multiplications, and the parasite load is decreased logarithmically. So this is the frequency of distribution in vitro pyrimethamine and sulfadoxine resistance in different time frame. Here we have seen sky blue color, that is Kolkata, represents Kolkata, and dark blue, that is represents Purulia. And we have seen from the year 2008 to 2013, the year-wise distribution of pyrimethamine resistance. Similarly, we have also found Kolkata, which represents brown color, and Purulia represents the green color. This is the year-wise distribution of sulfadoxine resistance. So again, distribution of different DHFR polymorphisms and their subsequent haplotypes in Kolkata and Purulia before and after introduction of national drug, that is ACT. Here we also seen that blue color, that is DHFR, that is 51I and 59R and 1089 gene mutation was subsequently increased, and we have also found that AN-RNL haplotype and AI-RNI haplotype are very fatal and also increase in number. Here, occurrence of different DHPS polymorphism and haplotypes in Kolkata and Purulia. Here we also found at the position of 436A, 437G, and 545E codon are also increased in subsequent years. Not only that, the different haplotype like AGEAA, which is dark green color, and AGEAT, which is orange color, those are also increased in number. So these are this figure shows the relationship between the IC50 value of pyrimethamine and sulfadoxine and the DHPR genotype. Here, the novel mutation in the 108I and 51I shows very high IC50 value for pyrimethamine than normal mutant allele. So these are published in the International Journal of Antimicrobial Agents. So this slide shows the alteration in vitro IC50 values for cloaking against different DHPS haplotypes in Kolkata and Purulia. SP combinations appears ineffective for treating falciparum malaria as resistant sulfadoxine as well as pyrimethamine among the parasite population increased, which was alarming, which was very much alarming in West Bengal. And this red color mentions the different haplotypes and with greater IC50 values having AGEAT, AGA, and SGKJT. So this is the relation, this is the third page of our study that is very interesting. The novel genetic polymorphism of Kale's propeller domain associates with artemisinin combination therapy failure. So we followed the WHO guidelines. There are 4 important guidelines. Number 1, the presence of parasitemia at 72 hours. Number 2, with a parasite clearance half-life more than 5 hours. Number 3, persistence of a parasite survival rate greater than 10%, which is season phase of the malaria. And number 4, the presence of a mutation in Kale's 13 gene above the codon 440. So these 4 criteria we have followed. The 2 terminology is very important, that is ETF and LTF, that is early treatment failure, which artesunate kills parasites rapidly, that is within 5 to 6 hours. And 20 isolates showed early treatment failure. We have found and sequenced it, and we have found 20 isolates having shows the early treatment failure. And the late treatment failure, sulfadoxine and pyrimethamine are the long-acting drugs which acts 3 to 5 days, and recrudescence of parasite within 42 days was classified as the late ACT treatment failure. So recrudescence of parasites observed in 18 patients. So early treatment failure, 20 patients, and late treatment failure, 18 patients. So treatment failure in endemic area, 4 districts we have found, that is ETF, that is blue color, and LTF is pink color. We have seen in Kolkata and Purulia, the early treatment failure and late treatment failure is greater than the Bankura and Midnapur. And this study was published in the Clinical Infectious Disease in the 2019. Next slide, that is parasite clearance half-lives and percentage of patients. So we have found the patients having 5 to 5.9 hours, that is near about 10%, and 6 to 6.9 hours, that is near about 3%. So this study, these results was published in the New England Journal of Medicine in the 2018 379 volume. This slide shows the parasite clearance half-life and ring stage assay, that is RSA, ring stage assay. So we have found that the before 10% season phase and after 5 to 6.4 hours shows this red circle shows the drug-resistant patients. So here parasite clearance half-life in different KL3 mutations, we have found above this line, above the 5 lines, we have there's ring circles, blue circles, which shows the parasite clearance half-life greater than 5 and having the mutation at the 625 positions and 513 positions. These results also published in the New England Journal of Medicine. And we are the first group which report that malaria become resistant in the West Bengal as well as India. This is the first report from India. Ring stage survivability in different